In the video before, we talked about how to find the sample space for any given experiment, such as flipping a coin, rolling a die, finding the outcomes on a transcript, or determining the sample space for results of a football game. In this video, we're going to look at equally likely events. And so equally likely events is going to depend on knowing what the sample space is and being able to find the probability of an equally likely event. So to begin, if all outcomes are equally likely, then we have the formula right here. So whenever we say equally likely, we just mean that the outcomes have an equal chance of happening. So for example, rolling a die, each number has an equal chance of happening. Flipping a coin, each side has an equal chance of being landed on. And so we're going to apply this formula right here directly to some of our examples. So again, this formula right here is just the ratio of the number of outcomes in our event A out of the total total possible outcomes in the sample space. So some of the examples we'll be looking at would be something like this. So this is a very simple example. So let A be the event that you tossed a coin and it landed on tails. What is the probability of getting a tail? So here obviously we can answer this without plugging anything into the formula. We know that the probability of getting a tail is 50% if we were to flip the coin. Our second example is, let B be the event that you rolled a die and it landed on a 5. What is the probability of rolling a die and getting the number 5? Again, we know intuitively that the probability of getting the number 5 is 1/6 because each number has an equal chance of occurring. But we're going to actually demonstrate how we can use the formula to solve these answers. And again, we're going to begin with very simple examples and then we'll move on to harder examples. So in my whiteboard right here. So I added the equation right here so that we can just keep it in mind whenever we're working through these examples. So again, the probability of event A is equal to the number of outcomes in A divided by the number of outcomes in S. I like to use this notation right here. So probability of A is equal to the number of outcomes in A out of the number of outcomes in S. So this is the notation I use instead of writing everything all out again. So again, this formula here only applies if the outcomes are equally likely. So every single outcome has an equal chance of happening. So in our first example, we know that this is an equally likely example because each side of the coin has an equal chance of happening. So the first thing to do when we're trying to use this formula right here is first find the sample space. So here our experiment deals with tossing a coin. And A is the event that the coin lands on tails. So the sample space is a list of all of the possible outcomes that we can get from an experiment. So for rolling or for tossing a coin, the possible outcomes we can get are heads, tails. The second thing to do is determine the number of outcomes in S. And so since we have written out our sample space already, we know that the number of outcomes in S is 2. We know that A is the event that the coin lands on tails. So let me just define that as A equals tails. And then the number of outcomes in A. So to determine the number of outcomes in A, we're going to look at our sample space and we're going to find how many outcomes in the sample space actually satisfy our event A. So if we look here, there is only one outcome out of the sample space that satisfies our event A. So number of outcomes in A will be 1. So just one outcome. So now we can plug it into our formula. So P of A, which is essentially the probability of getting tail, That's equal to number of outcomes in A over number of outcomes in S, which is 1/2. And this agrees with what we know intuitively. In our next example right here, we're considering the experiment where you roll a die. And here we know that the experiment, or all of the outcomes, are equally likely because each number on a die has an equal chance of happening. And so again, we begin with defining the sample, or listing out the whole sample space. So for rolling a die, the possible outcomes that we can get are the numbers 1 through 6. Which means that the number of outcomes in S is 6. B is the event that the number lands on a 5. So the number of outcomes in B, if we look at the sample space, how many of these outcomes actually satisfy our event B? So here, only one of the outcomes satisfy our event B. So number of B is 1. So if we plug it into the formula, P of B, which is equal to the probability of getting a 5, that's going to be number of outcomes in the event B over number of outcomes in the sample space, which in this case is 1 over 6. And this agrees with what we know from earlier in this video. We said that the probability of rolling a die and getting the number 5 is 1/6. Here, we used a formula and demonstrated that that is true. So these are some fairly simple examples, but moving on to this next example here, it's going to get a little bit more complicated. So here, we're stating that a family has 2 children. Suppose that the probability of having a boy or a girl is equally likely. That is, suppose that the probability of having a boy is 50%, and the probability of having a girl is also 50%. So here, we know that this problem is equally likely because it's stated specifically. We want to find the probability that both children will be girls. So the first thing to do again is to start off with the sample space. What are all of the possible outcomes that we can get for the 2 children? So one of the possible outcomes we could get is this family could have a boy, and then their second child is also a boy. Another possible outcome we can get is that the first child is a boy, the second child is a girl. We could also get that the first child is a girl, the second is a boy, or we could get that the first and second child are both girls. Here we have a complete list of all of our possible outcomes, and we find that the number of outcomes in S is 4. A is the event that both of the children will be girls. So let me just define what A is. A is the event that both children are girls. So now to determine the number of outcomes in A, we have to look back at our sample space right here. How many out of these 4 outcomes satisfy our event A, which is having both children that are girls? Only 1. So the number of outcomes in A is 1. Plug back into our formula, P of A, which is probability of both girls, that's equal to number of outcomes in A all over number of outcomes in S, which is 1 over 4. So the probability of having both children be girls is 1/4. Our following example is asking us to find the probability that one child would be a girl and the other child is a boy. So here we're dealing with 2 children. The sample space is still going to be the same, except that now we have a different event. We're looking for the probability that one child will be a girl and the other is a boy. So let me call that my event B. So 1 girl, 1 boy. Now to determine the number of outcomes in B, we have to again look at the sample space right here. How many of these outcomes satisfy having one girl, one boy? So we have this outcome right here. We also have this one right here. So there are 2 outcomes that satisfy being one girl, one boy. And then if we just plug it into the formula, P of B, which is probability of having one boy, one girl, that's equal to number of outcomes in B all over number of outcomes in S, which is going to give us 2 over 4, or 1/2. So as we can see here, the probability of having one boy and one girl is greater than the probability of having 2 girls. Now finally, moving on to our last example right here. So this is going to be probably one of the hardest examples we'll go through. You probably won't have any examples this hard on your exam or quizzes. So here we're considering the experiment or the event where you rolled 2 fair 6-sided dice. We want to know what is the probability that the sum of the 2 dice is 7. So the first thing I always recommend doing is listing out the whole sample space. So what are some possible outcomes for rolling 2 dice? So it's possible that the first dice lands on the number 1. The second dice also lands on the number 1. It's possible that the first dice lands on the number 1. The second dice lands on the number 2. 1, 3, so on. The list becomes really, really big. And so instead of writing out the whole sample space, let's go ahead and just determine how many outcomes would be in the sample space. And so a shortcut that I have for this would be the following. So here we're considering 2 dice, but for determining the number of outcomes in the sample space, we're going to look at a base to a power. The base will always be the number of outcomes for a single dice. So in this case, there are 6 outcomes for a single dice. And then the power will be how many dice or how many dice you have. So in this case, we have 2 dice. So 6 outcomes, 2 dice. If we solve this through, so 6 to the second power is going to give us 36 outcomes in the sample space. Now for A. So A, let's call it, A is the event that the sum of the 2 dice is 7. Let's list out all of those possibilities. So it's possible that the first die is a 1, the second die is a 6. That will give us a sum of 7. It's possible to get the first die a 2, the second die a 5. That will give us a sum of 7. 3, 4, 4, 3, 5, 2, and then 6, 1. So these are the outcomes or the combinations that satisfy our event A, which is getting a sum of 7. So here we can see that number of outcomes in A would be 6. So plugged into our formula, P of A, which is sum equal to 7, that's going to be equal to number of outcomes in A over number of outcomes in S, which is 6 over 36, which simplifies down to 1/6. So the probability that the sum of the 2 dice is 7 is 1/6. And again, the shortcut that I have right here will always work as long as you know how to apply it. So if you have 3 dice instead, it'll be 6 outcomes to the 3rd power. If you have 10 dice instead, it'll be 6 outcomes to the 10th power. If you had a different example where you were looking at flipping a coin, then for flipping a coin you have 2 outcomes, and then the power would depend on how many coins you have. So I hope this video has been helpful on the section 5.2 material.